Hello and welcome to Mr. Linford's math course. In today's discussion, we're going to be exploring the process of solving linear equations in a single variable where they have rational coefficients. In particular, we're going to learn about this method called clearing fractions and clearing decimals as a way to make these equations easier for us to solve. In this talk, we're going to go through and explore and define what a rational coefficient is, and we're going to review the process of clearing fractions and clearing decimals. First, we should identify what a rational number is. A rational number is a number, so we're going to say it's a number that can be written, let me rewrite that here, can be written as a fraction with integer numerator and denominator. So let's review what that means. A rational number is a number that can be written as a fraction. But I went and I provided a little more information here. It can be written as a fraction, and that's key, but this fraction has to be in a specific format. So this format says you need to have integers for the numerator and denominator. I guess as we're trying to define a rational number, we should probably define what's an integer. Well, an integer, those are positive and negative whole numbers and 0. So integers are the numbers 1, 2, 3, -1, -2, -3, 0, etc. Okay, so they're positive whole numbers, negative whole numbers, and 0. 0 is also an integer. So when we're going to write a fraction, we need to have positive or negative whole numbers for the top and the bottom number. So what are some examples of rational numbers? Well, something like a half, right? That is an integer. That 1 is an integer, and 2 is an integer. And the symbol for integers, remember for real numbers, we had this R, the bold R for real numbers. The symbol for integers is actually a bold Z. And to show a bold Z, we include this kind of line break in between the two parts of the Z. So both of these, 1 and 2, are integers. Let's talk about another one. Let's say 3/4. 3 and 4 are integers. Let's mix it up. Let's have -5/6. 1 negative, 1 positive. They're still whole numbers, so we're good there. That's a rational number. What about something like 0/7? That's actually a rational number too, because 0 is an integer and 7 is an integer, so we're good there. Could we have something like 7/0? Well, no, we can't have that, okay? That's part of the definition of rational numbers. It's kind of implied because really a rational number implies division. Anytime you have a fraction, right, we're implying division, and you can't divide by 0. So we're not going to have 0 in the denominator. So that should always be a special condition that we should always just assume with these numbers. So we're pretty good with these rational numbers. What about something like, oh, I got an example. What about 7/1? Is that a rational number? Well, 7 is an integer. 1 is an integer. So yeah, this would be a rational number. But isn't 7/1 the same thing as just the number 7 by itself? Yes, it is. An integer in this case, 7 is an integer, but 7/1 is also a rational number. And by the way, the symbol for rational numbers, rational numbers, is a Q. Don't ask me why. I don't really know. But the symbol for rational numbers is a Q. And we use a bold Q. We include these little lines inside of the Q. So that's the symbol for it. And what this shows us is really that different numbers can belong to multiple categories, okay? Every single integer, let me try to make a little diagram here. Every single integer, every whole number, is also a part of the rational numbers, okay? So let's say this box represents all the rational numbers. This circle represents all the integers. Every integer is also a rational number, right? Just pick any whole number, 5. You can write it as 5 over 1, okay? There, it's a rational number. Not every rational number, though, so for example, like 5, but not every rational number, let's say 1/5, not every rational number is a integer, okay? So every integer is a rational, not every rational is an integer. Hopefully that's making sense to you. But this is just the simple definition. A rational number, something that can be written as a fraction, but it has to be whole number numerator, whole number denominator, positive or negative or 0. Now, I specify this because I always tend to have a student who might say, when they're thinking of rational numbers, they might say something like, oh, pi, right? The number pi is rational because I can write it as pi over 1. There, it's a fraction. Now, careful. 1, that is an integer. But pi, that is not an integer, okay? So this is why pi actually is what's called irrational. An irrational number is just a number that's not rational. It's a number that can't be represented as a fraction. Pi cannot be written as a fraction, so it's irrational. So that's why we're not going to include it in this list. Other popular irrational numbers, the number e, Euler's constant, square roots, any square root that doesn't give a perfect square, like the square root of 2, square root 3, square root 5, etc., etc. These are all irrational. There's no way you can actually write them as a fraction. There's a fun little proof of this that I believe goes back to actually ancient Greece. If you're interested, I would definitely say look that up. It's somewhat manageable for students at an algebra level to read through and kind of understand what's going on. But if you'd like, feel free to talk to me about that. I'd love to share that with you. So, we have this understanding of what a rational number is. Think a fraction. Now, we want to figure out what to do when we incorporate fractions into equations. Take a look at this equation here. That does not look fun, right? Because, anytime we see fractions pop up and we know we have to work with them, we suddenly start getting a little queasy. It starts to get unpleasant. And why is that? Keep in mind, when you're working with fractions, you have to do a lot of work. You got to think, okay, if I'm going to try to combine them together, I need to have common denominators. So if I was to go and try to solve this, we could add 1/4 to both sides. And then maybe I could subtract a half x from both sides. 1/4 plus 1/4 is 2/4. 1/3 x minus a half x. Oh, well, these don't have the same denominator, so I'm going to have to make common denominators, and then I'm going to have to multiply by the reciprocal. Oh, gosh, this is just getting kind of messy, isn't it? It's not impossible, but gosh, it just seems super tedious. So instead of doing our standard method of solving an equation, instead of just brute force going through, making common denominators, combining fractions like we know how to do, why don't we try something different? Let's see if we can manipulate this equation to make it a little nicer for us. What I mean is, we don't want to have to work with fractions. We're lazy, right? Mathematicians are notoriously, we like to work smarter, not harder, let's say. So let's try to work smarter with this. We don't like working with fractions because it takes up a bit of time. And if we got to do a lot of these problems, we'd like a nicer, quicker way to solve these. So what could we do? What I want you to do is take a minute, pause the video, and try out a couple different ideas. What could we do to solve this problem without having to work with fractions? What could you do to manipulate this equation to no longer have fractions? Okay? Think back to what we know. The only techniques we have for solving an equation, we know that you can add whatever you want to both sides, and you can multiply whatever you want to both sides. That's pretty much it, right? I mean, there's the distributive property, but those are really the only two properties we have for solving an equation. You can add whatever you want to both sides, and you can multiply whatever you want to both sides. It just has to be the same thing that you multiply and add to both. So think about that. We have those two properties for manipulating an equation. How can we use one or both of them in some combination to try to get rid of the fractions? That's our goal. So pause the video, take a couple minutes, and go ahead and give it a try. All right, well, hopefully you had some time to work this out, and hopefully you came up with a couple different ideas. One of the things that we want to do when we say get rid of the fractions is we want to get rid of the denominators, right? That's the thing that makes it a fraction. We want these to be whole numbers. So we'd like the denominators to ideally all be a 1, right? Or just get rid of all of them. So what could we do to change all of the denominators so that they just cancel out, so they become a 1? Well, one of the things, we could add something to both sides, but would that really help us if I add a number to both sides? Well, not really, because if I add something to both sides, see how one of these numbers deals with an x and one of them doesn't? Those aren't like terms. So if I add something, it's not going to combine with both of them. Adding stuff to both sides probably isn't going to help us out. Let's think about multiplying. What can I multiply to both sides of this equation that would make the denominators cancel out? That would turn all of the denominators to like a 1, right? Well, if I multiplied by a number that was big enough to divide all of these out, that should work, right? What I mean by that is, think about if I had 1/3, let me rewrite that. If I had 1/3 and I multiplied that by 3/1, don't the 3's cancel out and we're just left with 1/1 or 1 itself? So that would also work out if I had something like 4 and I multiplied it by 4/1. Or if I had a half and I multiplied that by 2/1. That would cancel the denominators out. And if I picked other numbers, bigger numbers, let's say I took 1/4 and I multiplied that by something like 8/1, that would become a 2. The 4 would cancel out and the 8 would simplify down to a 2. I want to pick a number that's big enough where it cancels out the 3, the 4, and the 2. So what number is big enough that 3, 4, and 2 are all multiples, are all, I should say, factors of it? 3, 4, and 2 all multiply into this number. What is that? Well, hopefully, you're saying the number 12. What's a common denominator between 3, 4, and 2, or a common multiple? The number 12 is. So take the number 12, and we're going to multiply it to both sides of the equation. So I went and I multiplied this number to both sides. Allowed to do that. That's the multiplicative property of equality. You can multiply whatever you want as long as you do it to both sides. Now, I'm multiplying the entire side, the left side and the entire right side, by 12. That means I'm going to have to distribute it through. I'm going to have to multiply it to each thing. So I'm just going to show all of my work here. 12 times 1/3 x minus 12, or 12/1, times 1/4. Oh my gosh, my stylus, of course, now is quitting on me. So I like to show all of my work for this, especially if you're new with this concept. I think it's good to always write out all of your work when you're first exploring a new topic, because that way, one, you get more practice with it, and two, if you make a mistake, it's much easier to see where you might have made that mistake if everything's written out, because otherwise you're committing a lot to memory. That's where mistakes tend to happen, and we tend to forget then later on. So anyways, I just took this 12 and I distributed it to each of the terms. I'm multiplying every single thing by 12. So let's see what we have here. 12 over 1 times 1/3. That's 12 over 3. And there's an x there. 12 over 1 times 1/4 is 12 over 4. And then I have a 12 over 2x. And a 12 over 4. I didn't simplify anything yet. All I did was multiply fractions. And how do we multiply fractions? We multiply across. Let's see what happens now. What's 12 divided by 3? That's a 4. What is 12 divided by 4? 3. 12 divided by 2 is 6. And 12 divided by 4 is 3. Look what we just did here. We took this equation that had all fractions in it, and we have just turned it, we've manipulated it in a way so that we ended up with whole numbers. This is the technique of clearing fractions. If you want to get rid of the fractions, which really means you want to get rid of the denominators, multiply both sides by a number big enough that it cancels out all of the denominators, okay? That's the goal here. So to get rid of the 3, the 4, and the 2, we multiplied by a number that all of them went into. And how do you find that number? Well, just find a common denominator. Pretend you had to combine the third, the fourth, and the half, and you had to make a common denominator. Well, what's the smallest common denominator? 12 is. So that's the number you want to multiply by. By the way, you could have multiplied by other numbers than 12. There are other numbers that 3, 4, and 2 go into. Think about 24, right? 3, 4, and 2 also go into 24. They also go into 36 and 48. So you could pick any one of those numbers that you wanted, right? It's just, if you tend to pick bigger numbers, you're going to end up with bigger numbers to be working with, and that's fine. We have calculators, but typically we like to pick the smallest common multiple that they all share. So that's the idea. And this is something that's going to be really important, especially when you get into higher level math and you start working with fractions that have polynomial denominators, when you have rational expressions, we call them. So let's go ahead and solve this. It becomes very simple. I'm just going to add 3 to both sides to get rid of that 3. I'm going to subtract 6x from both sides to move that over. Let's see, 4x minus 6x is a negative 2x. 3 plus 3 is 6. And if I divide both sides by negative 2, we end up with x equals negative 3. And it's easy as that. Really, this is not that complicated of a topic, right? We're being very clever in just using this property, the multiplicative property of equality, that says just multiply whatever you want to both sides, as long as you do the same thing to both. We're using this property to make work easier for ourselves. I mean, yeah, I wrote several steps down. So what? That wasn't that difficult. Really, I just multiplied by 12 to everything, and then all I had to do was divide 12 by 3, 4, 2, and we're good. So this is a really helpful concept. I'd like you to start using this when you come across equations that have fractions in them. It's a good technique to have down. Let's go ahead and let's actually identify what process we used for this. So I would say step 1, find, I'm going to call it the least common multiple, or sometimes we can call it the common denominator. Basically, find a number that all of the denominators are factors of, that all the denominators multiply into, okay? Step 2, multiply this number to everything. Okay? You're multiplying it to the entire left-hand and right-hand side, meaning every single term you have to distribute that 12 through to. So once you find that number, go ahead and multiply it to everything. And then we'll just say, step 3, simplify. And once it's simplified, you solve it. Easy as that. So hopefully this is making sense. What I'd like us to do is to take some time to work on some practice problems. These problems are a little more in depth, but not too bad. What I'd like us to do is try working through problems that now have multiple things in the numerator, basically an expression in the numerator, multiple terms, okay? Again, you know the technique of if you want to get rid of those denominators, you know what you have to do. So go ahead and give this a try. Be careful with your work. I want you to pause the video, try this out, really show all of your steps in your notes here, because you want to make sure, especially with the problems that have subtraction to them, you want to make sure you're distributing everything properly. So that's my advice. Go ahead, pause the video, and let's see what you come up with. All right, well, hopefully you're able to get through these problems not too bad. I'd like to go through each one individually, starting with number 1. Let's take a look here. Let's take a look here at x plus 1 over 4 plus x plus 2 over 6. Oh my gosh, this stylus. I really need to get a new one. I've been saying that for the last however many years I've been making these videos, and I still haven't gotten one. All right, so we have this problem. We need to get rid of the denominators. So we need to multiply both sides of this equation by a number big enough to cancel out the 4 and the 6. So what number is that? What's a common denominator for 4 and 6? Let's see. 12 is a common denominator. So is 24, so is 36, etc. So which one do we want to work with? Well, I guess we could work with 12, since that's a fairly small number. So I'm going to multiply both sides by 12, and let's see what we get. I'm going to show all of this distribution, because I need to multiply 12 to this first fraction, and then to the second fraction. So 12 times the x plus 1 over 4, plus 12 times x plus 2 over 6 equals 12. Okay, couple ways of going about simplifying this. And you decide which way you like. When we're multiplying fractions, we know we have to multiply across. You multiply the numerators and you multiply the denominators. So you could write this as 12x plus 12 over 4 plus 12x plus 24 over 6. Again, I'm just distributing the 12 into the numerators again. Then what you would have to do is you'd have to divide each of these numerator terms by the denominator. So you would have to have 12x divided by 4, which is 3x, and 12 divided by 4, which is 3. That can sometimes be a little difficult for students. Sometimes this is a common answer I would get. A lot of times I'll see when students take 12x plus 12 over 4 and they want to simplify that, they'll divide the 12x and the 4, they'll divide that to get 3x, and then they'll forget to divide the 12 and the 4, and they'll just give me 3x plus 12. That's not actually how it's done. When you have 12x plus 12 over 4, that's the same thing as 12x over 4 plus 12 over 4. So it's 3x plus 3. You have to divide the other term by 4 as well. You have to do that. You can't just ignore it. It doesn't just get canceled out after you divide it the first time, okay? So that's one technique you can do, where you distribute it through completely and then simplify. I like to do things a little differently because I just think it's a little neater, and sometimes it's easier for students when they're working through so they don't make that simple mistake of forgetting to divide. What I like to do is actually swap the denominators. I like to swap the 1 and the 4 because they're going to multiply anyway, so just multiply the 1 and the 4 already. Why not? And then don't multiply the numerators just yet. You can do that. You're totally allowed to. It's the same thing, isn't it? So once I have this done, right, once I've already multiplied the denominators, now it's easier to simplify this. 12 over 4 is 3, and 12 over 6 is 2. So that's the technique I like to do. You'll see this on the answer key for the homework, this method of where I just move the denominator out. Again, you decide what you like to do. If you like to do the first method, totally fine. Just make sure you don't make that mistake with the division. So once we have this, it's pretty easy to solve. 3x plus 3 plus 2x plus 4 equals 12. Okay, I'm going to need to clear some space here and give myself enough room. So let's go ahead and we'll work up here now. Let's see. 3x and 2x are going to combine together to be a 5x. 5x, there we go. And then the 3 and the 4 are going to combine to be a 7, and that's going to equal 12. So if I subtract 7 from both sides, I end up with a 5x equaling 5. Divide both sides, x is equal to 1. So there's my solution for the first problem. X is equal to 1. Now that we have this technique for simplifying when you have multiple things in the numerator to work with, why don't you pause the video again, just take a couple, like 30 seconds or a minute, go back through and just check over your work. Check these other two problems, make sure that you did in fact divide properly, or maybe you want to try this new method, okay? All right, now that we have seen the first technique where we go through and move the denominator out to simplify it, I'm going to keep using that method for this problem. So let's work on x minus 2 over 5 minus x minus 4 over 2 equaling 2. Here I'm going to multiply both sides again. This time I'm going to multiply by a different denominator because, let's see, I got 5 and 2, so what's a common denominator for 5 and 2? How about 10? That's a number they both go into. So let's multiply both sides by 10. So I have 10 times x minus 2 over 5 minus 10 times x minus 4 over 2 equaling 20. Okay, I'm going to go ahead and move the 5 out, so I have 10 over 5 and x minus 2. And then I'll move the 2 out to get 10 over 2 and x minus 4, and that's equal to 20. Well, 10 divided by 5 is 2, and 10 divided by 2 here is 5. There we go. It's as easy as that. This went and just simplified it down totally very simple. I mean, this took, what, 30 seconds to do? And now it's a much easier problem to solve. So let's go ahead and distribute the 2 through. 2x minus 4. And then, let's see, a 5x, and we got a negative 20 equaling 20. Oh boy, I ran out of room again. That's okay, I'll just put my work up here. So the 2x and the negative 5x here is negative 3x. The negative 4 and the negative 20 is negative 24 equaling 20. I can add 24 to both sides. Negative 3x equals 20 and 24 is 44. And x, if I divide by negative 3, I get negative 44 over 3. I'm just going to leave it as an improper fraction. I like improper fractions. They're fine. I always wonder, what's the point in converting to a mixed number? We can do that later. So I just am fine leaving my answer as an improper fraction. So we have negative 44 over 3. Oh, wait a minute. That's not right. There's an error somewhere here. Oh no, what did we do wrong? Because the answer shouldn't be negative 44 over 3. That's not going to work out. So help me out here. What did we do wrong? I must have messed something up somewhere. So take a minute, pause the video. You can see all my work here. See if you can spot where the mistake was made. All right, did you catch it? Let's go ahead and see. So the first step, and multiplying both sides by 10, that's totally fine. And let me change colors here so we can kind of highlight what we're doing. First step's totally fine. You can multiply both sides by 10. We're allowed to do that. Let's see on the next step. I distributed the 10 through to each of the fractions. So it's to fraction 1 and fraction 2. And I made sure to multiply it to the other side. So we're good there. All we did was distribution. We moved the 5 out. And we moved the 2 out. So we ended up with a 2 and a 5. Yeah, we're allowed to do that. That's totally fine. So what's the issue? What did we do wrong? Are you seeing it? The main issue occurred right here in this step. Notice that when I distributed, because we had this set of parentheses here, and I carried the 5 through, I didn't distribute a negative 5. I multiplied so we had negative 5x and negative 20. I didn't actually carry the negative 5. So here's the issue. Negative 5 times x is negative 5x. Negative 5 times negative 4 is a positive 20. Remember, when we went over the distributive property, you have to make sure that you distribute the sign along with it, okay? One of the reasons I like this method of moving the denominators out, you end up seeing much clearer that you have a number with a negative on the outside of the fraction. Sometimes, or outside of the parentheses, sometimes if you don't do that method, if you just went ahead and distributed the 10 and then simplified, sometimes people forget, wait a minute, I should really be distributing a negative 10 through. So something to keep in mind and something to be careful for, okay? But I think that's this technique I'm showing where we move the denominator out will help us to prevent those mistakes. So now that we know that this should be a positive 20, let's try to fix up our work here. So instead of having a negative 24, I have a positive 20 and a negative 4. That's a positive 16. Okay, so if I subtracted that from both sides, 20 minus 16 is a 4. And then if I divided by negative 3, I would have negative 4/3. That is going to be our solution. Okay, now that we are starting to probably feel a bit more comfortable with this process, of this idea of moving the denominator out, and we're seeing, oh, we have to be really careful when working with subtraction, hint, hint, go ahead and check over your work for the next problem. Go ahead and see how you're doing, see if you're being careful with distributing signs, and then we'll come back and check our work. All right, let's go ahead and give this problem a try. We're going to move through it fairly quickly, so keep up and follow along. We need to first find a number big enough to cancel out 6 and to cancel out 3. What's a common denominator for 6 and 3? Well, 6's. Yeah, that's actually pretty easy. So I'm going to multiply both sides by the number 6. So we have 6 times 3x minus 2 over 6. I'm just going to hold off on the actual multiplying for right now, just so we can see how everything is being distributed. And then x minus 1 over 3. You can see I multiplied each thing by 6, and I made sure to also include that subtraction sign because we're going to need it. All right, let's go ahead and let's move the 6 out. And let's go ahead and we'll move the 3 out. And what do we end up with? Well, 6 divided by 6, that's just a 1. So we're left with 3x minus 2. 6 times 1 is 6. And then here we have 6 divided by 3 is a 2. And x minus 1 is what's left in parentheses. So we're going to have to go ahead and do distribution. And hopefully you're seeing we have to distribute a negative 2 through. So negative 2 times x is negative 2x. Negative 2 times negative 1 is a positive 2. All right. Hopefully we're getting pretty comfortable with catching this negative, and it's starting to make sense. We can go ahead and finish this problem pretty quick. We have a 3x minus 2, negative 2x. The 6 and the 2 makes an 8. Let's see, I'll move this up here. So let's see, 3x. If I added 2x to both sides, I should get a 5x. If I added 2 to both sides, I should get a 10. X equals 2. So that's the correct answer here. X is equal to 2. This technique, again, we're going to be using it quite a bit in this class as well as in future math and algebra courses. One of the things that we can do, though, for accounting for negatives, let's say you're thinking to yourself, Linford, I'm going to make the mistake of forgetting to distribute a negative. And you know what? I'm going to be honest with you. I do that all the time. It happens. Well, I don't do it all the time, but I have in the past. Yeah, I've forgotten to distribute a negative before. If I've done it in class, students tend to catch and they're like, oh my gosh, Linford, you forgot to distribute a negative. But it's so easy to happen just because sometimes we're just not paying attention to our work and we kind of skip over it. One of the things you can do, if you're thinking, oh my gosh, I might make that mistake, I might go ahead and actually forget to distribute the negative. There is something you can do in these problems to prevent yourself from even having to work with that. And it's pretty simple. What you could do, because this is the thing that might be throwing us for some trouble, go ahead and add this fraction. Oops. Come on. Go ahead and add the fraction x minus 1 over 3 to both sides. We're left with 3x minus 2 over 6 plus x minus 1 over 3 equals 1. This and this will be the same thing. They're going to give you the same answer. And this is totally allowed. Now we no longer have a subtraction sign to worry about. So if you're thinking, oh gosh, I might make that mistake, I might forget to distribute negatives, you're like, I know myself, I just know that's something I always struggle with, go ahead and, manipulate this to begin with. Go ahead and just move this over so that way you don't have to work with the negative. Just something to think about. Okay. Hopefully this is making sense to you. We're getting along here pretty well. What I'd like to do is take some time. I want to finish this video up. We're going to come to clearing decimals in the second part of this video. But for right now, let's go ahead, take some time, work on practicing solving equations that have fractions in them by clearing fractions, okay? And we'll get to decimals at another time. If you have any questions, feel free to let me know. My email is klinford, that's KLINFORD, at wccnet.edu. And until next time, take care.